So in our other videos, we went over gas laws having to do with the volume, that if the pressure changes, it changes the volume. If the temperature changes, it changes the volume. And if the number of moles of the gas changes, that changes the volume as well. Then we went over what if the volume stays the same and the pressure or the temperature changes. So if the volume stays the same, if the temperature changes, the pressure changes. But what if we have a problem where the volume, the pressure, and the temperature all change? What if we have all these moving parts and they're all changing? Well, that's where the combined gas law comes in, where we've combined all of these gas laws on the left into one mathematical formula that takes into consideration if the pressure and the volume and the temperature all change. Now, something I want you to notice with the combined gas law, if we look over here at the volume gas laws, the first one we see is P1 times V1 equals P2 times V2. And if we look over here at the combined gas law, we see on the top of the fraction bars, P1 times V1 equals P2 times V2. And if we look at the second volume gas law, the second gas law about volume, we have V1 over T1 equals V2 over T2. And if we look over here at the combined gas law, we see V1 over T1 equals V2 over T2. And if we look at the pressure and temperature gas law, we see P1 over T1 equals P2 over T2. And if we look at the combined gas law, we see P1 over T1 equals P2 over T2. So as you can see, this literally is the combined gas law. This takes the gas laws that you've been learning and it's combined all into one mathematical formula. P1 times V1 over T1 equals P2 times V2 over T2. So now let's try a practice problem with this combined gas law. 500.0 liters of gas in a balloon. So in a balloon, so that means the volume is going to change. It's going to expand or contract because it's a balloon. So the balloon is not a rigid metal container that doesn't expand and contract with the volume. This balloon means the volume is going to expand or contract. It's going to get bigger, it's going to get smaller. So 500 liters of a gas in a balloon is prepared at 700.0 millimeters per mercury, which is a unit of pressure, and at 200.0 Celsius, which is a unit of temperature. When the temperature cools to 20.0 degrees Celsius, the pressure of the gas is 30.0 atms. So you see this atms is the second pressure, and the 700.0 millimeters of mercury is the first pressure. And it's asking what is the volume. So what is the new volume? What is V2? So let's go ahead and take inventory of what we have. First we have 500.0 liters of gas. So that's going to be your first volume. That's going to be the volume you start with. So 500.0 liters. And that's the same as 500,000 milliliters. And then our first pressure, our P1, is 700.0 millimeters of mercury. And as you can see, I put a conversion key over here to my right. 760 millimeters of mercury equals 1 atmosphere, and we need to change this into atmospheres. So if we take the 700 millimeters of mercury divided by the 760 millimeters of mercury, we're going to get 0.921052632 atmospheres, and that's our P1. And then our temperature one, the temperature we started out with, is the 200.0 degrees Celsius. So 200.0 degrees Celsius, and to translate that into kelvins, we need to add 273.15. So that's going to equal 473.15 kelvins is our temperature one. And then the question asks when the temperature cools to 20.0 degrees Celsius, so that's going to be our temperature 2, our second temperature, and that's 20.0 degrees Celsius. If we change that into Kelvin, that's going to be 293.15 kelvins. So when the temperature cools to 20.0 degrees Celsius, the pressure of the gas is 30.0 atms. So that's going to be our P2, our second pressure. And that's already in atms for us. So 30.0 atms. And then it asks what is the volume. So our V2 is going to be our question mark. So that's going to be our X. So now I've rewritten this nice and neat over to the right hand side so we can figure out this problem on the left. So we have V1, P1, and T1, and our V2 is X, that's our question mark, and then we have P2 and T2. So using the combined gas law of P1 times V1 over T1 equals P2 times V2 over T2, we get 0.992105262 atms times 500,000 milliliters over T1, which is 473.15 kelvins, equals P2, which is 30.0 atms times X over 293.15 kelvins. So if let's multiply this P1 and V1 first. So 0.921052632 atmospheres times 500,000 milliliters is 460526.316, and that's all over 473.15, and that's equal to 30.0 atmospheres times X divided by 293.15. So let's take 30.0 atmospheres divided by 293.15, and we get 0.10233668, and then X times X. Now let's solve this left-hand side problem, this 460526.316 divided by 473.15. So on the left, we get 973.3199112. And that's equal to the 0.102336668 times X. So if we divide both sides by that number, That's going to give us x because these will cancel each other out, leaving x by itself. So 973.3199112 divided by 0.102336668 is going to equal 9510.958448, and that's in milliliters is our volume. If we want to change this to liters, we just move the decimal point over 3 places, and so that's going to be 9.51 liters.